Alvin Ssali, and this is my presentation concerning the AI assignment. Starting off with hill climbing, it's a local search algorithm used to optimization problems. Well, hill climbing starts an arbitrary point in the solution space, and it moves to neighboring solutions that offer better value depending on the objective function. Well, and then after that, it continues climbing towards better solutions until it reaches at a peak. And at this peak, the well-known neighboring states of an improvement. So hill climbing can get stuck in local optima. You can think of local optima as points in the search space that appear optimal or seem to provide optimal solutions compared to the nearby solutions but are not the best. A scenario in case for hill climbing, you could think of organizing a community event and what to minimize the travel time for attendees. So hill climbing can help optimize the placement of these venues to reduce overall travel distance, and by evaluating nearby locations, it can get to select the best one for you. Then I got simulated annealing, a probabilistic technique for group optimization that mimics a process of solid cooling metal where a metal as it cools, the atoms get to settle. So similarly with this algorithm, it usually accepts our solutions to explore the search space more broadly. But as the temperature cools or as the algorithm progresses, it becomes more selective and focuses on refining solutions. Well, unlike hill climbing, simulated annealing can escape local optima, and this is achieved by allowing suboptimal moves early on. So the likelihood of accepting one solution decreases over time, and will, of course, eventually the algorithm provides a good solution. So a scenario in case you could think of optimizing bus routes in a city, so method annealing would explore various routes, initially accepting suboptimal ones first to explore more possibilities and, of course, avoid getting stuck in local optima. But as the algorithm keeps on progressing, it becomes more focused on finding the most efficient route. And then genetic algorithms, these ones here simulate to mimic the process of natural selection and evolution. They maintain a population of candidate solutions and evolve these solutions over generations using strategies like crossover. A crossover is combining solutions into a better solution, then mutation, applying random changes to a solution, selection, choosing the best performing solutions. A scenario in case you could think about resource distribution to various regions after a disaster. So suppose this aid needs to be distributed to various regions after a natural disaster. With constraints in mind, such as distance, demand, and available resources, genetic algorithms can involve different allocation strategies to find the most efficient and distribution plan over time. Then improving local search algorithm is built with responsible and explainable AI. We all know that responsibility focuses on fairness, transparency, and accountability in AI systems. So, for example, in genetic algorithms for the resource distribution plan, so response AI integrates ethical constraints and ensure equitable distribution, avoiding biases. And for explainable AI, it ensures transparency in AI decisions. It gives reasons why an algorithm performed this decision. So with explainable AI integrated instrumented annealing, it would clarify why a particular bus route was selected, showing trade-offs like reducing time travel. Adversarial search for it, it's used in competitive environments where we have agents we can know them well as players having conflicting goals. So it aims to find optimal strategies for a player by considering both his or her moves and, of course, with the opponent's counter moves. Two scenarios you could think about in a marketing competition between two companies. So the first adversarial search can help one company anticipate the marketing moves of its competitor and develop counter strategies to mitigate the counter moves of the opponent company. And then for cybersecurity, firewall defenders through adversarial search helped anticipate hacker strategies that help preventive action strengthen the system against such attacks from hackers. And then minimax and expect minmax algorithms. Minimax is used in two-player zero-sum games where one player's gain is directly the other player's loss. Yeah, that's a relationship. So it varies the best possible move for a player by assuming the opponent will play optimally always, and the goal is to maximize the player's minimum possible gain, so hence known as minimax. Yeah, an example is in chess. Minimax algorithm evaluates each potential move by considering how the opponent might respond, aiming to minimize the loss or maximize the gain for the given player. And then expect minimax, it introduces the aspect of probability into minimax, and this involves chance. So it accounts for randomness in addition to players' actions, incorporating probability into decision making. An example in Monopoly, the expect min-max algorithm would account for the randomness of dice rolls and help decide to optimal decisions based on, of course, both chance, probability, and the opponent's actions. And then alpha beta pruning, for it just prunes away branches of the tree that are known to be relevant. So in this, it gets up to speed up the search process, making it an essential component for the game playing AI. An example is just in chess game. If one move is guaranteed to be worse than a previous evaluated move, that branch is pruned, so that algorithm needed to go there and examine it further. This saves computational effort. Then adversarial machine learning, this involves techniques where attackers write full AI models by feeding them deceptive data. So attackers alter input just to make models produce incorrect results. An example I've given here, an attacker just added some small changes to a dog image and then fed it into an AI model, and then the AI model had to misclarify the dog image as a cat image, just due to an adversarial attack. And then a relationship between adversarial machine learning and adversarial search. Both adversarial machine learning and adversarial search involve competing agents with conflicting objectives. And adversarial search agents attempt to maximize their ability while minimizing their opponents. So they maximize their satisfaction while minimizing their opponents. Just like in adversarial machine learning, one attacker tries to confuse the model and the defender or the model itself tries to maintain accuracy. Thank you very much.